All right, everyone. Welcome to our ACOM seminar today. It's my great pleasure to introduce Bill Randel. Bill's the section head of chemical climate here in ACOM, and he studies anything and everything related to dynamics and transport in the upper troposphere and lower stratosphere. And I think what sets Bill's research apart from a lot of other dynamicists is that he actually makes a lot of use of observations, including tracers, to understand the atmosphere. Bill's the first person I really met at NCAR through the COSMIC program when I was working on cosmic data as a master's student. And this is fun because it's sort of full circle now. Bill's also in the COSMIC program and is here today to discuss some findings from the new COSMIC-2 mission. So Bill, take it away.
Thank you, Nick, and hello, everybody. Am I good here?
Yes.
Okay. Hey, one thing Nick didn't mention from my resume is that I was on Nick's PhD committee at CSU, number one, and number two, I was on Nick's hiring committee in ACOM. So I'm coming full circle with Nick also. Okay, so today I'm going to talk about COSMIC-2 radio occultation data, and I share a part-time appointment in COSMIC. And let's see, I need to say thank you to these people at the bottom here. So Fei Wu has done all these calculations, everything you'll see today. Fei has done that. Aurelian is a colleague in Paris. He's been a visitor to ACOM a number of times. Rolando has helped a lot in interpretation of these results. Janet is a scientist in COSMIC. And I should also just thank COSMIC colleagues for helping me stay involved with COSMIC. Okay, so let's see. I'm trying to advance my slides and they're not advancing. Oh, here we go. Okay, so I'm going to talk a little bit about introduction. I'm going to give you a brief overview of some active science topics in the UTLS and the role of GPS data. And then I'm going to work my way toward showing you some new results from COSMIC-2. And I'm going to talk about waves in the tropical tropopause region, planetary-scale equatorial waves. I'm going to talk a little bit about diurnal tides, and I'm going to end up talking about small-scale gravity wave features. Okay, so this is a kind of a cartoon to start off looking at the tropical UTLS. So this blue region here is the upper troposphere, lower stratosphere. That black horizontal line is the tropical tropopause. And these are some of the interesting things that happen in this region. It's influenced from below by deep convection. There's a lot of clouds and cirrus and aerosols in this region. A lot of mixing from the mid-latitudes, two-way mixing from the tropics into mid-latitudes and vice versa from baroclinic eddies and monsoon circulations. There's lots of waves in this region. These kind of these blue arrows I've added to this plot. And these waves are important for a number of things, but most important for clouds in this region, for dehydration. And it's a source of forcing for the waves that propagate vertically into the stratosphere and higher, and they force and drive the quasi-biennial oscillation and the semi-annual oscillation. The upward transport near the tropopause is important for setting the background composition for the stratosphere, and in particular, it sets the water vapor values. And we've been interested in that topic for some time, and have used GPS data for that project, for that problem. And this is just one slide, kind of showing a highlight slides from our work, looking at the control of the water vapor in the stratosphere by the tropical tropopause cold point temperature, in particular as measured by GPS. So this plot shows a time series over about 13 years of the gray line is water vapor in the stratosphere, and the red line are effectively GPS temperatures. And you can see extremely high correlation, and the physics here is simply that the air is crossing cold point, tropopause, and dehydrated to whatever temperature is going on there. And this is a very simple and powerful explanation for control of the stratospheric water vapor. I mentioned the forcing of the QBO and the SAO. The QBO is a particularly hot topic right now. And I took this nice picture from Rolando and Yaga's paper last year or so, where the NCAR can now, the Wacom is one of the handful of models in the community that can accurately model the QBO or realistically model the QBO, kind of from first principles. So this is a comparison of the observed QBO, and these are zonal winds over the equator for about 20 years. And the lower panel shows the Wacom QBO simulation in this 110 level high resolution model. And in that model, the oscillation is driven by the resolved equatorial waves, and this is a 1-by-1 simulation. And those waves in that simulation are driven by convection run in the model. And about half of the forcing for the QBO comes from parameterized gravity waves. And this is, as I said, this is one of a number of models in the community that can do this. It's maybe one of the best models, probably, as typical for Wacom. But this is a comparison. There's a lot of work in the community, as I said. There's something called the QBO initiative, a comparison of models that simulate the QBO. This is a paper last year from Laura Holt showing inspecting the waves in these models that have resolved QBO. So there's a dozen models here, and there's observations in the lower right. And what these are pictures of the power spectrum of precipitation in the models. And it's the precipitation and the latent heating from precipitation that drives these large scale waves in the model that propagate into the middle atmosphere and drive the QBO. So if you want to have a good QBO, you want to have a good precipitation spectrum in your model, a realistically forced one. And you can see here, Wacom compares reasonably well to observations. And there's a number of models you can see here that don't have very much power in precipitation, and they have different QBOs, maybe aren't as realistic. So this is all to motivate you about why we want to study waves, but I want to highlight also the QBO has undergone a couple of recent disruptions. And if you're not an aficionado of the QBO, it was discovered in about 1960 or so, and ever since 1960 till early 2016, the QBO was very regular, progressing from the middle stratosphere downward, about a 2-year period. It was very regular for these 55 years or something. And then 2016, there was a disruption. In 2020, last year, there was another disruption. So we had 55 years of regular behavior, and then 2 of the last 5 years have had this disruption. It's not regular in these years. So this is even making this topic even more interesting in the community. Okay, a little bit more of why we're interested in waves near the tropopause. I'm going to show this model results from Uyama et al. And Eric Jensen's involved with this. And this is a model to simulate, to realistically simulate clouds and water vapor near the tropopause. And it's a curtain trajectory model. So this model runs many trajectories backwards and forwards in time, and incorporates waves from the reanalysis, but also artificially gives stronger wave amplitudes because the reanalysis don't capture all the small scale waves. And so I've shown an example here in the lower right of what a TTL cirrus is. These are features near the tropopause, and they're very frequent. This picture in the lower left here is the climatology from the space LiDAR. And you can see about 30 or 40% of the time you see these cirrus. They're important for radiant balances and understanding water vapor dehydration. And you can see this model on the upper left. This is their model results. It compares quite favorably to the Calypso measurements. And then they can play with this model and figure out the different sensitivities. And the key point here is that the waves, these additional small scale waves they impose in the model are very important. And you need these additional waves to realistically simulate the cirrus clouds near the tropopause. So we want to know what those waves are as best we can is the short story here. And one more thing I'll show you here is that this is a separate study that's come out recently, but it's looking and looking at their relationship to GPS temperatures. And the key point of this figure is that you have cold anomalies occurring in these GPS temperatures right about the time and place where you have these space LiDAR observations of the cirrus. So this is a very causal mechanism that's showing that GPS temperatures can help explain the formation of these cirrus. And lastly, I just want to highlight this balloon mission that flew last year in the tropical UTLS. It's called Residual 2. It's a joint France-US mission. They flew 8 long duration balloons in the tropical tropopause layer. And each of these flew for about 100 days, and they're all instrumented, completely instrumented. They measure water vapor and CO2 and ozone, aerosols, LiDAR measurements of the aerosols, and the data I'm going to show you overlap, the GPS data overlap this time frame. So we have high resolution satellite data that overlap these balloon measurements. There's going to be 2 more of these balloon flights happening in 2021 and 22 and 24 and 25. So actually this fellow that's a co-author with me, Aurelian, is part of the team that's analyzing these data. So we're collaborating on those. Okay, so I'm going to get in now to the GPS or the Gnss radio occultation. And basically the short story is, many of you are familiar with this, but there are constellations of radio emitting satellites circling the Earth. Your GPS in your car or your telephone works with these. And then there are some low altitude satellites that intercept these radio waves crossing through the atmosphere, the limb of the atmosphere. And these waves are bent and slowed down a little bit by the atmosphere, and you can back out very accurate temperatures. You can back out electron density in the ionosphere, and you can back out water vapor measurements in the lower atmosphere. The temperatures turn out to be extremely high quality. They're long-term stable. They don't care about the weather. The radio waves go through clouds. They're very high vertical resolution. This is one of their key attributes in the tropics, something like 1 kilometer vertical resolution and very high accuracy. The average profiles are better, something like 1/10 of a Kelvin. So GNSS has been flying for some time. There was this is a plot showing the number of radio occultation measurements over time. So COSMIC, or the COSMIC group, the UCAR group, has been involved with this from the very beginning. They were involved with this GPS MET proof of concept mission back in the middle 1990s, and showed that this technique worked well. And beginning in about 2002, there's been continuous global measurements. This CHAMP was the first satellite. It's a German satellite. And then in 2006, the COSMIC-1 constellation was launched with 6 of these little receiver satellites, and it flew for over a decade. You can see that blue curve kind of decreases over time, and that's when different satellites kind of fall off the record. But it continued till the late 2010s, and then in 2019, the COSMIC-2 constellation was launched. And COSMIC-2 is improved over COSMIC-1 in terms of higher quality antennas and receivers. It also can track not only the GPS constellation from the United States, but the Russian GLONASS constellation, and potentially the European Galileo constellation of the GPS emitting satellites. And so you get about, here we get about twice as many measurements. We get something like 4,000 to 5,000 measurements per day, occultations. And the other strength of COSMIC-2 for this work I'm going to talk about is that these measurements, this is a low latitude constellation focused on the tropics, low latitudes. So you can see this picture on the right shows the number of measurements as a function of latitude. So COSMIC-2 is focused more or less between 40 north to 40 south, a very high number of measurements in time. Okay, and it's just a pretty picture on the left here. It was a nighttime launch. I did not go to this, but the COSMIC colleagues went along and had a great time watching the satellite launch. And picture on the right just shows the sampling from one day. This gives you a feeling for the number of measurements. And again, each one of these measurements is very high quality, high vertical resolution. And I should also just mention here, there's also a growing constellation of commercial GPS radio occultation receivers, and these are being incorporated. COSMIC is being incorporated in all the weather forecasting centers, as are these commercial satellites, commercial GPS data. Okay, so now I'm going to get into what I'm going to talk about in detail. So I'm going to talk about some of the early COSMIC-2 data and applied to the tropical UTLS. And I'm going to look at temperatures, just temperatures today. And these temperatures basically go from about 10 kilometers up to 30 or 40. I'm going to focus on 10 to 25 or something. And I just show there on the right just some examples of what temperature profiles look like, just a spaghetti plot of 20 profiles or something. And you can see the UTLS region, the minimum temperatures there get below 200 degrees, a lot of wavy variability. And this is not noisy behavior. This is geophysical, it's geophysical noise. It's actual waves in the atmosphere. So what I'm going to do is we're going to look at data for 6 months. Again, I've shown you there already, there's something like 4,000 to 5,000 occultations per day. And what we've done is derived a gridded data set. And this data set is 4 by 10 degree latitude. And we have so many data, we can do this at 6-hour resolution. And I'm doing this because I want to look at the tidal oscillation or tidal variability from a 6-hour resolved data. I'm going to apply space-time spectrum analysis to these gridded data. And I'm going to talk about the resulting equatorial waves and tides that come out of that. And then I'm going to talk at the end a little bit about the leftover from the gridded, what I call residuals or small scales. And I'm going to try to convince you that these have some, these are actually also geophysically relevant quantities, and they look like gravity waves, but we'll get there in a little bit. Okay, this is just, I'm going to show you just now an example of one day of how we do this gridding. So this picture on the left is all the measurements, all the little plus signs are all the measurements for one day, January 10th, between 8 degrees north and 8 degrees south. The temperature is at 18 kilometers. And then that black line is kind of the smooth fit through that. You can see there's large scale wave structure there. And there's lots of variability about that black line. And that's the small scale stuff. So the picture on the right shows a grid for this day. And you see these features in the tropics. So there's this relatively high temperatures near 90 degrees east, and then low temperatures near 180. And these are, you can see they're centered on the equator. These are Kelvin waves. And I'm going to, these planetary scale waves, they propagate regularly eastward. And this is just an example what they look like for one day. This is what the variance of the temperature looks like at 18 kilometers over the equator. So the black line is the total variance. And what I mean here is the total, I'll go back to this figure, just take the variance in about the zonal variance of all those little points. That's the total. I can also look at the variance of that fit through there, the black line, that's the gridded variance. And then the leftover, the difference between those two is the residual. Okay, it's the small scales. And so the thick black line here shows the variability of all the variance. And so there's a few peaks throughout the year. Most of this variance is captured in the gridded product. So these are large scale, mostly Kelvin waves. And the red line here shows this, the leftover or the residual variance. I'll come to that at the end. I'm going to try to convince you it has some real geophysical structure. It's as big as the gridded variance when the gridded variance is not large, but the gridded variance has episodes, it's forced by convection, and then it gets much larger than the residual. Okay, so here's a so-called Muller diagram. So on the left here, it's time versus longitude of the temperature anomalies at 18 kilometers. And what I want to show with this picture is these eastward propagating planetary scale waves. These are Kelvin waves. And I've taken a picture, a snapshot on the right of one day of what this Kelvin wave looks like as a function of altitude and longitude. And what you see are eastward tilting planetary scale features with there's a vertical wavelength of something like 6 kilometers here. These waves modulate the altitude and temperature of the tropopause, and they kind of just regularly propagate around. If you stare at this figure on the left here for a while, you can see these waves, they get excited in December and they more or less propagate around the world three or four times continuously during this period we're looking at. And just because this is a chemistry seminar, I don't have much chemistry, but I thought I would show, or at least say, that all these features we see in GPS temperatures or many of them are often observed in ozone data. So all these wave variability near the tropical tropopause, it's a separate seminar, but they're also reflected in ozone measurements or other constituents with vertical gradients. So this is, again, just this comparison of the temperatures on the left, these Kelvin waves propagating eastward and mirrored in ozone data. But I won't talk any more about ozone today. Okay. So I'm going to show some space-time power spectra. And before I do that, I'm going to talk a little bit about equatorial waves. And there's a vast literature on equatorial waves, and a lot of people spend much of their careers understanding and evaluating equatorial waves in models and data. But this is kind of a background of equatorial waves are basically the normal modes of the atmosphere in the tropics, and these were figured out in the early 1960s. Very famous Matsuno paper. And well-known dispersion relation for a number of waves in the tropics that are either symmetric or anti-symmetric about the equator. And I've circled a couple of them here. There's this Kelvin wave. The picture on the upper right is the structure of the Kelvin wave. It's symmetric about the equator. It sits on the equator and it moves eastward and is typically planetary scale, very low zonal wave numbers. There are a number of anti-symmetric, or I'm sorry, the westward moving waves also. The kind of well-known feature is the mixed Rossby gravity wave. It's an anti-symmetric mode. So what that means is the temperatures on one side of the equator are opposite to the temperatures on the other side of the equator. Right at the equator, there's very little, zero temperature anomaly. And these like to move westward. And you can also have Rossby waves that move westward, and a whole series of inertial gravity waves that move both eastward and westward. And as I said, these are kind of well known in the meteorological community. This is a very famous paper by Wheeler and George Kalatis showing the power spectrum of outgoing long wave radiation, or basically it's large scale tropical convection. And this is looking at data for many years, but what they were very clever to figure out is that the power spectra themselves are very red, most of the power is at low wave number and low frequency. But if you can take that away and look at the bumps in the spectrum, so look at the ratio of the spectrum to the smooth background, you get what I've shown here. And in that case, all of these waves that I showed you in the last figure come out very clearly. So you can see on the left there in the symmetric waves, symmetric about the equator, you see the Kelvin waves stand out, these equatorial Rossby waves stand out, and some of the westward inertia gravity waves stand out. So these, again, these are the waves that are symmetric about the equator, centered on the equator. And then there's a whole series of anti-symmetric waves that are out of phase across the equator. And in particular, the mixed Rossby gravity wave, that moves westward, and the eastward inertia gravity wave that moves eastward. And then some of these westward inertia gravity waves. So this is kind of the spectrum from the convection. Okay, so now I'm going to show you similar figures from COSMIC-2. Now, this is a very or somewhat different calculation. I'm not showing you ratios of power to some background. I'm showing you the full power here. So these are actually the temperature power spectra. So what we've done is we've taken 120 days of the COSMIC-2 data, this gridded product I've shown you, 4 degrees by 10 degree lat long grids every 6 hours, and done a cross spectrum analysis in zonal wave number and frequency. And we can plot the symmetric part and the anti-symmetric part. And it's color coded, and these are log contours. So the red is 10 times bigger than the yellow, et cetera, or 100 times bigger. And a number of features pop out to your eye. So on the symmetric on the left, we see Kelvin waves are the dominant variability that are symmetric. And again, I showed you this in that Muller diagram a few slides ago. You see that clearly with your eye, but now it comes out very clearly in the power spectra. You can see Rossby waves, low frequency Rossby waves. You can see some higher frequency things. You can see this N=1 inertia gravity wave moving westward with just about a 2-day period, and very strong tide, 1-day period, tide feature comes out. So this is a zonal wave number 1 with a 1-day period moving westward, and so-called DW1. The anti-symmetric waves look a lot like I showed you before. If you have if your eye is trained for such things, you go, this makes complete sense. You see a very strong mixed Rossby gravity wave here. You see these N=0 inertia gravity waves, and these follow along. I didn't point this out, but these black lines are those same dispersion curves that I showed here and here. So the fact that these observed waves fall along these dispersion curves is agreement with very simple theory. These numbers here, 4 and 8, refer to the vertical wavelength of these dispersion curves. So this mixed Rossby gravity wave fits pretty well with theory for about a 6 kilometer vertical wavelength, and likewise for this Kelvin wave. Okay, here's another way to look at this. So we have these beautiful spectra now. We can slice and dice them a number of different ways. So here's a slice where we've added the zonal waves 1 to 6 all together, but now we look at the power in the lower stratosphere as a function of latitude. And I've got labels on here for these various features. So the biggest feature in the tropics is this Kelvin wave. It's symmetric about the equator. You can see this mixed Rossby gravity wave. It's anti-symmetric, so these blobs here are out of phase with each other. There's this N=0 inertia gravity wave. There's a weak maximum here and a weak maximum in the other hemisphere. Those are also out of phase. There's this N=1 inertia gravity wave, has a weak maximum on the equator. The tide, the westward migrating tide, jumps out of this in this figure, mostly centered in low latitudes. And then lastly, we also see this very interesting 1-day eastward tide features that it's bigger amplitude in the outside of the tropics than it is in the tropics. This is an eastward so-called non-migrating tide. We'll talk more about that in a bit. But you can just see this beautiful amount of information that comes out of just kind of these, these raw temperature measurements. Okay, and here's just one further way to slice the data. So now this is looking at the power of the symmetric components and the anti-symmetric components on the right as a function of altitude between 10 and 30 kilometers. I've drawn in where the tropopause is there. So you can see the Kelvin wave on the left and the n=1 inertia gravity wave that can kind of stand out along with the tide in the symmetric part. In the anti-symmetric part, the mixed Rossby gravity wave and the n=0 inertia gravity wave also stands out in this diagnostic. Okay, I'm going to talk a little bit about comparisons with Wacom. So what we've been able to do is Rolando and Yago were generous to share that result. I showed you early on in the talk. I won't go back there, but it's very, very high quality simulation of the QBO in Wacom, this 110 level Wacom, and they archive the data. So we were able to go back and actually do the identical analysis to the Wacom data that we did the COSMIC-2, taking 6 hourly samples. So we can kind of do a pretty much an apples to apples comparison. Now we don't expect, this is not for the same time period. This is the free running Wacom. So we don't expect exact correspondence to the exact waves, but the comparison here is intended to see if the, the qualitatively how does the Wacom power spectra compare? So this figure on the left is what I've shown you already, the COSMIC-2 spectra, and the Wacom result is on the right. And the take-home message is that the large-scale waves with labels on them are reasonably well simulated in Wacom. The Kelvin wave, the mixed Rossby gravity wave, even these small amplitude inertia gravity waves, and even the tide is quite well simulated in Wacom. You can see overall Wacom is blue compared to the C2 power spectrum. And what that means is that there's less power in the higher frequency Wacom variability. And this is kind of a well-known, I won't say problem, but a well-known aspect of Wacom, and it's related to the lack of high frequency variability in the precipitation, in the convective or the parameterized convection, if you will. There's a lack of high frequency variability, but the large scales are quite reasonable, I think. Oh, I should also say, note here that these eastward tides that we surprisingly see in the COSMIC-2 spectra, they're not evident as big features in the in Wacom. And here's just a second comparison. Again, now these are altitude versus frequency. The top is C2 data, the bottom is Wacom, and I got symmetric things on the left, anti-symmetric on the right. They look overall very reasonable. You can stare at this for a while. They're quite interesting to look at all these details. The details for these large scales are quite well simulated. And I think the conclusion I take away is that these Wacom does this 1 by 1 degree, 110 level Wacom does quite a good job at the large scale waves. Okay, a little bit about the tides. So these tides are very interesting. We haven't been able to have high enough quality data or frequent and dense enough data to really carefully diagnose these tides. So these are the tides in the COSMIC-2 data. On the left, I've got this westward wave, so-called DW1. It's wave number 1. It's kind of follows the sun, so it's so-called a migrating tide. You can see it peaks, it starts to have big amplitude just above the tropopause, and it grows with altitude into the lower stratosphere, or even when you can't see, higher into the atmosphere, and it gets to be quite big at higher altitudes. The eastward waves on the right are, they turn out to be not one zonal wave number, but waves 1 through 4, and they turn out to be out of phase between the hemispheres, are quite interesting. They're small in the tropics and they're big in the extratropics. We can't really go to higher latitudes with this cosmic data. I told you it's focused in the tropics, but this is kind of a new finding, and we hope to follow up and understand more. These eastward non-migrating tides become very large in the thermosphere and mesosphere and thermosphere, and they are a primary coupling mechanism between the lower and the upper atmosphere. So this is kind of one of the first looks at the sources of these eastward tides. Okay, I'm going to show you a kind of a complicated figure here, but I'm going to start with just a piece of it. So what we've been able to do is make maps of the diurnal tidal variability. So this is, we can do this for each 6 hours that we map the data. So it's a very simple calculation. We have these gridded products for every 6 hours throughout the 120-day record, and we just average these for every 6 hours. And so this is the map of the anomalies in temperature at UTC -6. And what you can see is a kind of a big blue blob over South America there, and a big red blob over Australia and Indonesia, kind of a zonal wave #1 feature. So this is the bottom, if you will, of the tidal feature in the lower stratosphere. This is for one snapshot. Now I'm going to add the other snapshots here. So this is, top is -6 hours and 0 hours, 6 hours and 12 hours, stepping through the day. And I've added in these solid and dashed black lines showing where local noon and local 6 p.m. is. And time goes downward. And you can see this, these patterns migrate in time, they move westward, and they amplify over the continents, which is really interesting. I think what physically was happening, these are responding to localized convection that has a strong diurnal cycle over the continents, especially over South America and Africa. And that diurnal cycle, that local diurnal modulation is embedded within this wave #1 pattern that moves westward in time, following the sun. This is really beautiful to me. I think we haven't been able to diagnose this before from cosmic or from GPS data. Okay, now I'm going to show you what Wacom looks like. Same, more or less the same calculation. And first of all, just look at the colors. And if I showed you this, the picture here at the top looks a lot like the Wacom picture at the top looks a lot like the cosmic picture at the top. Big blue blob over South America, big red blob over Indonesia. And actually, you stare at these for a while, and they all more or less agree between Wacom and COSMIC-2, which is really cool. The interesting part is I've cheated. I've moved the Wacom results by 6 hours. If I showed you this without doing that shifting by 6 hours, there's not very good agreement. For example, hour 0 here compared with hour 0 over here between Wacom and C2 is not a very good agreement. So this is kind of a new result. They're beautiful tides in Wacom, but they don't appear to mesh exactly. The phase looks different than cosmic. And I don't know, this might be a problem. We might have been reading the data wrong or doing our calculations wrong. We're exploring this. But the fact is these beautiful patterns exist. And well, it's, as I see at the bottom here, this is work in progress. And it's a new way to diagnose the model. We'll see how it turns out. Okay, my last topic here is I want to look at the leftover variability. So everything I've shown you so far is the result of these gridded data. So again, we do this gridding every 6 hours, and we can capture all this beautiful geophysical variability I've shown you. Now I want to look at the leftover, what we're not gridding or not mapping. So this, I've shown you this figure on the left here before. The black smooth line is the mapping, and the little pluses are all the individual measurements. And you can see there's a lot of variability about that black line. This is, again, I think this is not noisy data. It's geophysical structure, and try to convince you that a little bit. So one thing we do is just take that average of that residual and make a map of it. So this big color map in the middle is that residual variance averaged over this 120 days. And again, averaged over 18 to 20 kilometers in the lower stratosphere. And if it was just noisy structure, you would just see noise or maybe no structure. But instead, what you see here is geophysical variability. There's clear maxima over South America and over Africa, and this kind of more or less coincides with where the convection is occurring. The picture on the right shows a proxy for deep convection. There's a maximum in this residual variance over the equator in the tropics, not over these continents. And note that well, I'm going to talk more about that. And lastly, I just want to point out that there's very large residual variance in the extratropics, in particular, this big maximum over Asia during this season. And don't really understand this. This is a kind of a new finding, but it doesn't look noisy. It looks kind of geophysical. There's another maximum over North America. There's a maximum over South America down here. This is kind of a well-known hotspot for gravity waves over the Andes. So we kind of contend just from this map that there is coherent space-time structure in these small scales. It's not just noise. And kind of this is just early days, but I think there's a lot of work to do to understand the details of this small scale variability. Okay, the last little thing I want to show you is looking at the variability in the tropics here. So you'll see this maximum more or less over the equator. And note that the convection for this time is situated a little bit south of the equator. So this residual variance likes to be centered right on the equator. And I'm going to show you a series of figures to explore this a little bit. So this is a picture of that residual variance as a function of time and longitude. So we take, try to explain this. We take these types of these data, we calculate the variance of all these little pluses about the gridded field, and we can map that quantity in itself. And so this is what comes out of mapping that quantity. And so it's not random in time. You can see it actually moves eastward, and it's kind of regions of maximum variance that move eastward with time. They're stronger in the longitude 0 to 180. I'm going to keep that, and I'm going to put these black dashed lines over there, just kind of trace some of these maxima. And I'm going to show you on the left now, this is the figure I showed you early on. This is the Muller diagram of just the temperature anomalies, the gridded temperature anomalies. And what this shows is that these maxima on the right, if you will, these black dashed lines, I've just repeated them on the left, they like to occur right between the negative and positive gridded temperature anomalies. And this kind of happens throughout, more or less throughout the record. And what's going on is shown in this cross-section. So this is this cross-section I showed earlier of the gridded temperatures of the solid, and dashed lines here are the background Kelvin wave. And on top of that, these thick black dashed lines, or thick solid black lines, are this residual variance. And what happens is this residual variance likes to occur sandwiched right between these Kelvin waves, especially right in the tropopause layer. And the Kelvin waves propagate eastward, and these residual temperature anomalies propagate right along with them. And so that's one clue that it's not random variability. And so we stared at this for a long time and thought about ways that this could be happening. So I'm going to give you a hypothesis. We think now that this small scale variance is associated with gravity waves, and their amplitude is responding to variations in the background static stability as measured by this n squared, the Brooke-Weisler frequency. This is kind of getting into technical details for the experts here, but the left picture here shows you what I showed you already, the temperature residual variance in the black solid lines. The right panel shows for the same day where extra large values of the static stability occur, and in these red curves. And if you're an aficionado and you know these are contours above 8, and 8 is a big number. The climatology here is like 6, 5 or 6. So 8 is a big number. And what's happening is the background is being modulated by the Kelvin waves. So the combination of negative and positive Kelvin wave temperature anomalies provide a very strong enhanced n squared. And the enhanced n squared is related to the residual temperature variance. So that's one case. This happens actually throughout this data record. That's one event on January 14th. Here's a second event in March. Same diagnostics. Again, the black solid lines on the left are this residual variance. It's sandwiched between the Kelvin waves. The lower right is this enhanced n squared on this day. So why should these be related? The theory says, or the theory we're trying to follow says that if you have gravity waves excited by convection or whatever process, and they propagate into a faraway region where the stability is varying, the temperature variance should be proportional to the cube of n cubed. This is the theory. It should be a relatively simple relationship. The residual variance should be proportional to n cubed. And so this figure on the bottom, it's my last figure, it shows that this works in these data. So we've taken all of the residual variance, and what we've done is we've taken every longitude, so 36 longitudes per day, and we've co-located the residual variance at 18 kilometers and the value of n cubed at 18 kilometers. So there's 36 times 120 points in this plot. And what you can see is some pretty strong statistical relationship. There's a correlation of almost 0.5. And again, I could show you these types of pictures on the left for your eye. This kind of happens throughout this data record, where the residual variance is following these patterns of the large scale stability. So this is kind of a working hypothesis, work in progress type of thing, but it's exciting to see some physical explanation for the small scale variance. Okay, I'm done. My key points, my takeaway points are that COSMIC-2 is beautiful, excellent, high quality data. And I've just shown you temperatures, but it actually measures water vapor in the troposphere also. And it's kind of pioneering work we're involved with in COSMIC in looking at the water vapor at the same level of detail that I've shown you for these temperatures. So we have novel high resolution spectra. I've shown you these planetary waves and tides. It's very powerful data to compare and constrain the model, if you will, and evaluate models. And point number 3 is we're identifying and understanding these small scale waves. I think these results on the relation with convection and the relation with Kelvin waves themselves are pretty exciting, and there's work in progress. This detail on the tides and why they don't agree with Wacom, that's also a work in progress, and we'll update as time goes on. So thank you for your attention. I hope there's people still here, but happy to take questions.
Thanks, Bill. We will wait for some Slido questions to come in. So I have a brief question before everyone starts to trickle their questions in. I always had this mental block with the vertical resolution of COSMIC because it's always given very, very high vertical resolution, but then people throw on round numbers like, oh, it's a kilometer, effective resolution or something. So what is the actual sort of effective resolution of COSMIC-2, and is it better than COSMIC? How does it all fit together and work?
Yeah, it's probably 1 kilometer is a pretty good number, I think, for the UTLS region. And a lot of that has to do, I think, ideally, if you just look at one location, it theoretically can be much better than 1 kilometer, but effectively these are averages over 200 kilometers or something as a radio wave is transversing the atmosphere. So kind of the two-dimensional effective vertical resolution turns out to be something like 1 kilometer. The higher quality for COSMIC-2 really is probably going to be evident in the water vapor product in the troposphere. That's really where the focus is on getting profiles to go lower, but also having a smaller signal to noise rate or larger signal to noise ratio. And it's probably more important for water vapor.
Cool. We should do a regionally refined Wacom mesh on the equator and resolve some gravity waves, and we can figure out how bad Wacom is at resolving that structure that you're seeing in the Kelvin waves.
That would be wonderful. Yeah. Okay. Maybe we lost the chemist. I didn't have a hydrogen cyanide or something. So do we know if anybody was actually here?
I would hope so.
Okay, well, maybe I've explained everything so perfectly clearly. There's no questions.
Even your work in progress stuff is perfect.
Well, I reserve the option that we haven't done it right. So these title results are making me go back and wonder.
Oh, there we go. Now we have a question.
Yes, I agree with Rolando. These comparisons with Wacom are making me go back and worry a little bit about the details of our cosmic analysis. So I think the DW1 is probably not, well, we'll have to just see. And Rolando, I will follow up with you on this in more detail. But
okay, we'll hold for like 20 seconds more, maybe. If anyone else has any burning questions. Cool.
no, I think the latitudinal scale of Kelvin waves is more like 10 degrees, Joan. Yeah, observationally, it looks more like 10. I mean, these things go out to about beyond 10 degrees. So yeah, this is a good question. The relation between the Kelvin waves and the residuals, and are we somehow building in some of this structure from our analysis? I'm worried about this myself, and the reviewers of our paper are worried about this. So we try to address this as clearly and simply as we can. Yes, absolutely. We saw the mixed Rossby gravity waves, and we see equatorial Rossby waves, and yes, John, you missed them. I can send you the paper, and they're very, especially the mixed Rossby gravity waves are very strong, and they're kind of beautiful geophysically. They're these beautiful anti-symmetric waves propagating westward. The N cube comes from Fritz and Alexander paper, equation 55. And I haven't gone and looked up. I initially thought it should go like N squared, Rolando. And my co-author Aurelian tells me it should go like N cubed. And if Joan is still around, maybe she can explain why it should go as N cubed. But even if I showed you N squared, it's still highly correlated with N squared. I agree. I agree with this, but it's what a spectral thing. I don't know. You mean the N cubed? I don't know. It's as I understand, it's what you expect from shooting gravity waves propagating into a variable stability region.
I feel like this conversation needs like an actual Zoom meeting on itself.
Absolutely. Okay, maybe we can be finished here. I appreciate feedback and people paying attention here, and thank you. And thank you, Nick.
Thanks, Bill. Yeah,
okay.
Thank you. And thank you, Brett. Thank you, Brett and Marianne.
Yeah, thank you, Brett. Yep.
Helping out.
Bye.